1995 E2. They're giving us a circuit with a battery on the right, positive on top. They tell us numbers, the voltage, the resistance, the capacitor. They tell us that the capacitor has a dielectric of some kind of plastic in there, and this also indicates that we're going to start out uncharged because the switch is open. All right, they give us the dimensions of the capacitor. We have an area of a square meter. Sheet of plastic is a millimeter. They convert it for us. How nice of them. And then we measure the capacitance directly. Then for part A, they want to know what is the dielectric constant of the plastic. All right, so capacitance is kappa epsilon naught A over D. You can get this off of your equation sheet. You should also have it memorized. It was on that sheet that I wanted you to memorize, and then we ended up not having a quiz because school got closed. So you haven't had a quiz on this, unfortunately. So they want to know what kappa is. You can take this equation, rearrange it a little bit. CD over A epsilon naught. If you plug in all the numbers that they gave you, so 0.05 microfarads, and the distance is 10 to the minus third, and the area is 1, and epsilon naught is a constant of the universe, you're going to get a kappa of 5.65. Now, what are the units on this guy? There are no units on this guy. This is sort of like mu in mechanics. It's just a scaling factor for a material. All right, B part 1. They've given us information, the numbers there. They've reiterated some of these things. And then we close the switch, and then they ask us 4 basic facts about this circuit. So the initial charging current, remember when capacitors are uncharged, they act like a plain wire, and the current is due entirely to the battery voltage and the resistor. So the initial charging current is going to come from Ohm's law, which is V equals IR. And then they tell us what V is, and they tell us what R is, and I think that's a 6. So we get 1.5 times 10 to the minus 5th, and you need to have units on this because it's a numerical answer of amps. Part 2. What is the time constant? All right, time constant is RC, the resistor that is in series with the capacitor, because it's the resistor that's going to slow down the charging of the capacitor. And we have, again, 2 mega ohms times 5 times 10 to the minus, what is this? 4th? I think that's a 4th. 0.05 micro. That sounds about right. And when you plug those guys into your calculator, you get 0.1 seconds. Remember that the time constant is a measure of time. How long does it take for this circuit to charge up? All right, number 3, the magnitude and sign. All right, don't forget about that. The final charge on the bottom plate of the fully charged capacitor. All right, so the bottom plate, that will be negative. Because if you take a look, that is connected to the negative side of the battery. So we say by conventional current, the positive charges march out of the top, down the wire, deposit on the top side, set up an electric field that then drives a positive charge away from the bottom side and leaves behind a negative charge. So we're going to make sure that we need to have a negative there. And we want to know the magnitude also of that. The magnitude of that charge is going to be the voltage of the battery times the size of the capacitor. Plug in the numbers that they gave us, and we get to have 1.5 microcoulombs because we're going to have 30 times 0.05. All right, part 4. How much energy is stored in the fully charged capacitor? Well, that's going to be 1/2 CV squared. Or if you prefer, Q squared over 2C. Again, these two equations are equivalent. All we've done is substitute Q equals VC in to get rid of one of the variables. Once you plug in the numbers, so we'll have 0.05 micro, and then 30 squared, we will get an energy of 2.25 times 10 to the minus fifth, and energy is always going to be measured in joules. Now, what we're going to do is we're going to disconnect it from the battery and the resistor. So now we have this capacitor that's already charged, and now we're just holding it at arm's length, trying not to zap ourselves. Once we do that, we're now going to pull this plastic sheet out. We're not going to move the separation. We're not going to remove or add any charge. And then they ask us two questions about this. What is a new voltage across the plates? Well, if we go back to part A, this is a classic AP style question where you get halfway through the problem, and then halfway through the problem, they change the conditions on you. So you go back to part A, we're now going to be removing the capacitor, not the capacitor, the dielectric. We're going to be removing that kappa. So for part C, our C new is going to be the original capacitance, but with the dielectric removed. So the new capacitance is going to be divided out of that kappa, which we found to be 5.65. Now, if you look at B part 3, Q equals VC, this Q is a constant. That's not going to change. They've told us how they're going to change the C, so we have to figure out how V is going to change in response. So V original, C original equals V final, C final. Well, the original voltage was 30 volts because we connected it to a 30-volt battery and charged it up all the way. The original capacitance is 0.05 times 10 to the minus 6, 0.05 microfarads. We're looking for our final voltage, and they've told us how to figure out the final capacitance, 0.05 times 10 to the minus 6th over 5.65. You should notice that these two guys cancel out, and what we're going to end up doing is multiplying 30 times 5.65 to find that final voltage, which is 170 volts. 170 volts. All right, part D. Is there more energy? Where did it come from? If there's less energy, where did it go? All right, so for part D, I'll change color here, D. All right, again, with the changing of conditions and then asking us the same question about something, look at B part 4. We have a calculation of energy here, and now we know what the new capacitance and the new voltage is. So we can say U final is going to be 1/2 C new, V new, and don't forget to square that puppy. So we can plug in our numbers. 0.05 micro over 5.65 times 170 squared, and we can get a new number for it. And what you're going to notice is, yeah, we've made the capacitance smaller, but then we squared the increase. So U final is going to be greater than U original. Where did it come from? Work had to be done to remove the dielectric. All right, so let's come back over here and take a look at this. Let's blow it up, and I'll redraw my diagram that I drew in the notes with dielectrics. So the top plate has pluses, the bottom plate has minuses, and then in the middle here we have our dielectric, which is going to be polarized, but not let the charges move on it. So as it gets polarized, that means we have a bunch of minuses pulled close to these pluses, and then we have a bunch of pluses pulled close to these minuses. And when we're going to remove the dielectric, that means we're going to pull it to the side, so pull. So this pair of charges that are close, I mean all of these pairs of charges, but I'm going to focus on this one. This pair of charges that is a certain distance away, they're going to get pulled farther away. Pulling this minus sign away from the plus sign is going to increase the energy between them, because what they want to do is be close together. So this is sort of like taking a bowling ball and picking it up off the ground and lifting it up higher. You're increasing the energy by doing that. Remember that opposites attract. So if we pull this guy out to the side, this plus is going to pull on this minus, this plus on this minus, this plus, and the same thing on the bottom. If we let go, so if we eliminate this guy, this thing is going to get snapped back into the middle so that these guys line up across from each other again. That being the case, we had to do work to increase the potential energy between the dielectric that was polarized and the capacitive plates that were essentially fixed in place.